Okay, so let us now solve the exercises. So the first one asks us to find all the units in the ring of Gaussian integers. Find all the units in Ji. Being a Euclidean ring, this already has a unit element which is unit, but besides that we may have other units also. So let us see what we can do. Let a plus bi in Ji be a unit, be any unit in Ji. Then what does it mean? It means that a plus bi has its multiplicative inverse also in Ji. That is, there exists a Gaussian integer with which if we multiply a plus bi, then we will get 1, the unit element in Ji. So then a plus bi times c plus di equal to 1 for some c plus di in Ji. Okay. This implies, now if we take a complex conjugate on both sides, on the right hand side, since we have 1 which is a real number, so it will stay 1. On the left hand side we will have a minus ib times c minus id. And multiplying these two equations we get which is a plus bi times a minus bi times c plus di times c minus di. So this is 1 because both of them are 1. Okay, so finally we have got something that looks like this. Now because a, b, c, d, these are integers, these things a square plus b square and c square plus d square, these two factors are non-negative integers. In fact, they are both positive integers because their product is 1, so none of them can be 0. Since and c square plus d square are positive integers, we must have both of them should be equal to 1. We are not really bothered about the fact that c square plus d square is 1. We want to know about this because that's what we have chosen. Okay, so a square plus b square is 1. Thus we have only the following possibilities. Note that because a and b are integers, we can only have these cases. Say a can be 0 and in that case b is either 1 or minus 1. Yes, this is one possibility, and the other possibility is that a is either 1 or minus 1 and b is 0. So accordingly, what shall we have here? If a is 0 and b is 1, we have I. If a is 0 and b is minus 1, we have minus I. Similarly, for the second one, since b is 0, we will have either plus 1 or minus 1. Accordingly, a plus bi is equal to 1 or minus 1 or I or minus I. And we already know that these elements in Ji are units. Hence, the units in Ji are that completes the solution. So Ji has 4 units. As opposed to this, the ring of integers has 2 units, minus 1 and 1. So here we get 2 more additional units. Okay, then exercise 2. If a square plus b square is equal to 1, then a plus bi is a unit. Oh, sorry, what the hell am I writing? If a plus bi is a non-zero complex number and is not a unit in Ji. Herstein has the unfortunate tendency to be somewhat sloppy in writing these questions. You see, a plus bi not equal to 0 is not a unit in Ji. It actually means that a plus bi is already an element in Ji, although the sentence does not convey that information properly. But you have to understand that a plus bi is a non-zero element in Ji, and additionally it's not a unit. So that's what this means. Okay, so we have started with if, then prove that a square plus b square is greater than 1. Okay, that's what we have to prove. We have to prove that any non-zero non-unit Gaussian integer has its d value greater than 1. So in other words, if we use the contrapositive of that statement, we would say that if the d value of a Gaussian integer is equal to 1, then it must be a unit. And in fact, that is what we are going to prove now. Solution. Okay, some ink is needed. if a square plus b square is equal to 1, then okay, let us just see what happens if a square plus b square is equal to 1. We will later on we will see why we are starting like this. Then a plus bi is a unit, as we have seen in the previous solution. See, here we have in fact proved that if a square plus b square is 1, then a plus bi is a unit. So that means what? If a plus bi is not a unit and a plus bi is not equal to 0, then a square plus b square is of course neither 0 nor equal to 1. So since a square plus b square is the d value of a plus bi, it has to then be greater than 1. Since a plus bi is not equal to 0, the previous sentence is the contrapositive of the assertion in the exercise. And that's it, because we know that a statement and its contrapositive are logically equivalent. So this means that if a square plus b square is if a plus bi is not a unit in Ji, let us see what we have written is actually, let's just see once more. If a plus bi, okay, we have proved till this. If a square plus b square is 1 and a plus bi is a Gaussian integer, then it is a unit, that we have proved in the previous solution. Now we are having a Gaussian integer which is non-zero and it is not a unit, okay, then we have to prove that a square plus b square is greater than 1. Note that because a plus bi is non-zero, so a square plus b square cannot be equal to 0, because for this to be equal to 0, both a and b have to be equal to 0, but in which case a plus bi will be 0, which is not possible. So a square plus b square is a non-zero integer, and in fact that means it's a positive integer. Why? Because that is the d value of a plus bi, and we know that the d function gives us non-negative integral values. So since it has to be now positive, so it means it has to be greater than or equal to 1, okay, and this is coming only from the condition that a plus bi is not equal to 0, okay. Now if it happens that a square plus b square is 1, then we have seen here that a plus bi has to be a unit, but it is given that a plus bi is not a unit, so that hypothesis will be contradicted. That's why a square plus b square cannot be equal to 1. So it is not equal to 1 also, just like it is not equal to 0. So the only possibility is that a square plus b square has to be greater than 1. So that's how we get this solution. And this answers one of the questions that we were facing while we carried out one proof. So there we mentioned that in exercise 2 we will have this proved for us, and now it's over. Okay, then next exercise 3, this is computational. Here we will be given some Gaussian integers. We will be asked to find their greatest common divisors. Find a greatest common divisor of in Ji, that must be mentioned. Of these two situations, 3 plus 4i and 4 minus 3i. So this is one, and the other is this 11 plus 7i and 18 minus I. Now to actually find the GCDs, we will carry out that Euclidean algorithm. In fact, Euclidean algorithm means we have solved one exercise. Do you remember? After the section on Euclidean rings, after that we solved one exercise where there is an algorithm is given where you divide one of the numbers by the other, then the divisor is divided by the remainder if it happens to be non-zero, and we go like that until we till we get to the zero remainder. The remainder before that is the GCD, is a GCD. So that exercise we are going to use. We will however not mention that, we will just simply use it. Now in the first one is particularly easy. Let us see why. Note that (3 plus 4i) is equal to minus I times 4 minus 3i. Am I having it correctly? No, it will not be minus item, it will be I times 4 minus 3i. So this means that 4 minus 3i divides 3 plus 4i in ji. So that just simply means that 4 minus 3i itself is the GCD. Thus 4 minus 3i divides 3 plus 4i in ji. This implies 4 minus 3i is a greatest common divisor. But why? That you may raise that question. To answer that question, we do like this. You see, suppose you apply that algorithm. So according to that algorithm, we have to divide one of these two Gaussian integers by the other. I choose to divide, say, 3 plus 4i by 4 minus 3i, and in the first step itself we have got zero remainder because 4 minus 3i divides this one. So the previous remainder according to that algorithm will be a greatest common divisor. Now according to the way the algorithm goes, if we achieve division, complete division in the first step itself, then this itself is a GCD, because this can be regarded as the previous remainder. Although we don't have the step here if we get the job done in the first step itself, but if you go back to that exercise, you will see that Rn is considered to be greatest common divisor, and in fact Rn plus 1 was equal to 0 according to the notations of that exercise. And there you will see that if we have in fact made a comment in the solution also to that exercise, that what happens when we have division in the first case itself. There you will see that we have mentioned that the divisor itself becomes GCD. So this is the greatest common divisor, but there is one more thing to note. Since I is a unit, not only is 4 minus 3i a GCD, but 3 plus 4i is also a GCD. Why? Because you see, since I is a unit, you can multiply on both sides by the multiplicative inverse of I, which is nothing but minus I. If you do that, 4 minus 3i will be minus I times 3 plus 4i. So you can run the whole argument with the roles of 3 plus 4i and 4 minus 3i interchanged. So that will tell you that 3 plus 4i is also a greatest common divisor. That is one way of looking at it. The other way of looking at it is that once you have a greatest common divisor in a Euclidean ring of two elements, then you keep multiplying the GCD by units, you will get other GCDs. In fact, we have discussed about this when we studied Euclidean rings in general. So from that angle also you can think. So anyway, so here both this and this are greatest common divisors. Now we go to the second one. So far as the theory of Euclidean ring goes, greatest common divisor, prime elements, these actually have many, you can say, avatars. The avatars are obtained by multiplying them by units. You have got here one GCD, the other GCDs will be obtained by multiplying this one by unit. Just like that, if you have a prime element, you multiply that by units, you will get more prime elements, which are just like this one, but they are other flavors of that prime. Just like in the ring of integers, you have two units. So technically speaking, if p is a prime, then so is minus p. This is one prime with which you have the unit 1. This is another prime with which you have the unit minus 1. So units, the more units you have in a Euclidean ring, the more flavors of an element you will get. These are unnecessary things actually. We need not consider the other flavors. You will get exactly same results. So and that is why we have that equivalence relation of two elements being associates in a Euclidean ring to get rid of that triviality. Okay, now in this case there is a sequence of calculations. I'll just write the things. You can verify on your own whether these are true or not. Note that 11 plus 7i, it happens to be 18 minus I plus minus 7 plus 8i, and where, so here we have divided 11 plus 7i by 18 minus I. 1 is a quotient and this is a remainder. To make sure that this is a remainder, since it is non-zero, its d value should be less than the d value of the divisor. That must be written accompanying this one. So the d value of minus 7 plus 8i, which is nothing but minus 7 whole square plus 8 square, and it happens to be 113. So this is actually less than the d value of 18 minus I, which is 18 square plus minus 1 whole square, that is 325. Then in the next step of our algorithm to find GCD, we will divide 18 minus 7i by minus 7 plus 8i. Divide the divisor of the previous step by the remainder of the previous step. So doing that, we will get 18 minus I. Here, however, the calculation is not as easy as the other one, the previous one. It is minus 1 minus I times minus 7 plus 8i plus 3. In this case, the remainder turns out to be a real number. This is 3 square plus 0 square, which is 9, and that is definitely less than the d value of the divisor, which now is this. Way less than this. The size of the the d value will tell you how far you have gone in towards the completion, how close you are to the completion. So we have lowered the d value here significantly of the remainder, so we are close. And then after this we divide. Okay, so here the divisor is this one and the remainder is 3. So next we have to divide minus 7 plus 8i by 3. If you do that, you get minus 2 plus 3i times 3 plus minus 1 minus I, where the d value of minus 1 minus I is, of course, minus 1 whole square plus minus 1 whole square is 2, which is less than the d value of the divisor 3, which is 9. And finally we have to now divide 3 by this remainder, and that gives us minus 1 minus I times I minus 1, or because we are actually writing the divisor as the second factor, let me just maintain that minus 1 minus I plus 1, okay, where d of 1 is of course equal to 1. This is the smallest possible d value, because you see d value is defined only for non-zero Gaussian integers, and the smallest d value can be obtained the smallest d value that we can obtain is 1, and that, as we have already seen, happens only when the Gaussian integer itself is a unit. Okay, so in this case we have actually got 1 itself, and this is less than the d value of -1 minus I, the divisor, which is 2. Okay, hence, and after that you see, if you now divide 3 by 1, then of course the remainder will be 0. So that is the last step, but since that is obvious, so we are not mentioning that. So from here itself, that step will give us 0 remainder. So the previous non-zero remainder is 1. So that is the greatest common divisor. So hence 1 is a greatest common divisor of what were the elements 11 plus 7 9 and 18 minus I, that is 11 plus 7 I and 18 minus I are relatively prime or co-prime Gaussian integers. Okay, so this completes the solution. And then we go to the next one. So what does the next one have? Exercise 4. Prove that if P is a prime number of the form then there is no x such that x square is congruent to -1 mod p. So we remember that result, that lemma, the second lemma in this section, which says that if P is a prime of the form 4n plus 1, then this congruence is solvable. So this is just this is not a converse or anything to that lemma. Okay, is it a converse if x square? Anyway, so here the point is that if P is an odd prime not of the form 4n plus 1, then it has to be of the form 4n plus 3. Then this congruence is not solvable. Okay. And the solution, we are going to do a little cheating here. For the solution, we refer to C theorem 5.5 from Barton's elementary number theory. Okay, there it has been proved. So now you can ask me, why should we not do that here? We can do, but since at one point we are going to study number theory, so we don't want to repeat things. We should take the liberty, and if it is a form of cheating, then it's okay. We are cheating, and the subsequent few exercises will be like that. We will freely refer to results from Barton, because sooner or later we are going to have to start elementary number theory. algebra and number theory actually cannot be studied separately. They have to be studied together because they are deeply related. Anyway, so let us now proceed like this for a few more exercises. Exercise 5. Prove that no prime of the form four n plus 3 can be written as a square plus b square, where a and b are integers.